Hello everyone. Today we will discuss retractions and fixed points. So, in this section we will prove several classical results of topology, and that follow from our knowledge of fundamental group of S1. So firstly we define retraction. So what is a retraction? Let us say X is a space and A is a subset of X. Then a retraction mapping of X onto A and that is basically a continuous map, let us say R, from X to A, which is identity when we restrict it to A. So R restricted to A, this is identity map of A. So any continuous map from X to A, which is identity map when it is restricted to A, that is called retraction of X onto A. And if such a mapping exists, then we say A is a retract of X. Now we will prove that the homomorphism induced by inclusion map, that is injective, if the domain space is retract of the range space. So we prove this lemma. If A is a retract of X, then the inclusion map, then the homomorphism of fundamental groups induced by inclusion map, that is injective. So let us say this inclusion map is J from A to X. Then we want to prove that J star is injective. So let us prove this. Now that is given to us that A is a retract of X. So let us suppose that R from X to A, this is a retraction mapping. And we know J is inclusion mapping from A to X. So the composition R circle J, this is basically a mapping from A to A, and this is identity map of A. Because J is inclusion, so being inclusion map J of A is equal to A for every A in A, and R restricted to A, that is also identity, being a retraction mapping, so R circle J, this is identity map of A. And we have proved that if the mapping is identity, then the homomorphism induced by that mapping is also identity map. So it means R circle J star, this is homomorphism of fundamental group induced by R circle J. So this is also identity map. But we know R circle J star, that is R star circle J star, so it is identity map. If R star circle J star is identity map, then J star is injective and R star is surjective map. So J star is injective map. This we want to prove. So the proof is complete. Now using this lemma, now we will prove no retraction theorem. What is no retraction theorem? No retraction theorem says there is no retraction of B2 onto S1. There is no retraction from B2. B2 here is closed ball of unit uh, radius, and S1 is circle of unit radius. So there is no retraction of B2 onto S1. Now let us suppose R is a retraction from B2 to S1. We will prove it by contradiction. Suppose this be retraction of B2 onto S1. Then we define a mapping J from S1 to B2, which is inclusion map. So let J be inclusion map. Now from the previous lemma, this J star, this is injective. That means the mapping J star, which is basically from the fundamental group of S1, and let us say we take the point B0 to fundamental group of B2 with respect to say any point 0. So this is injecting map because J star is homomorphism induced by J. So this is injective. Now we know fundamental group of S1. This is additive group of integers. So this is infinite group. And we know fundamental group of B2, that is trivial, that just contains only one point, because we know when the space is simply connected, the fundamental group is just trivial. It contains only identity element. So B2 is simply connected space. So fundamental group of S1 is Z and fundamental group of B2 is 0. So we are saying we have a homomorphism J star from Z to 0, which is injective. But that is impossible because the domain space is infinite and the range space contains only 0, one element only. So we cannot define injective mapping from Z to 0. So that is a contradiction. So it means there is no retraction of B2 onto S1. So this is a contradiction which completes the proof of the result. Now we have a lemma. Now we prove some conditions which are equivalent to null homotopy of a map. So now in this lemma we assume that H is a mapping, continuous mapping from S1 to X, where S1 is a circle. So let this be a continuous map from circle to any topological space X. Then we prove that these conditions are equivalent. The first condition is H is null homotopic. Null homotopic means a map which is homotopic to constant map. H is homotopic to constant, it means. Second condition is H extends to a continuous map K from B2 to X. H can be extended to a continuous map K whose domain is B2. Means the mapping H which is defined on the circle, that can be extended to whole of the closed ball B2. So third condition is H star. This is trivial homomorphism, and H star is homomorphism induced by H. This is trivial homomorphism of fundamental groups. So let us prove this result. Now we prove here 1 implies 2. Means if H is null homotopic, then H can be extended to K, which is a continuous map defined on B2. So in the first condition, we are assuming H is null homotopic, means H is homotopic to a constant path, constant map from S1 to X. So let us take capital H is the homotopy. So let capital H is the homotopy between H and a constant map. So it will be a mapping from S1 cross I to X. Suppose this be a homotopy. And then we define a mapping pi from S1 cross I to B2 by pi of xt, that is equal to 1 minus t into x. This is for every x in S1 and for every t in I. And we know whenever x belongs to circle and t belongs to a closed interval 0, 1, then the point 1 minus t into x that lies in B2. So this mapping is well defined. Further, this mapping is continuous because it is 1 minus t into x. So by definition, we can easily verify that it is continuous and it is a closed mapping, and also it is surjective. And we know every continuous closed and surjective map is a quotient map. So it is a quotient map. And one more thing, it collapses uh, all of the set S1 cross 1 to the point 0, because when we take any point x in S1 and 1 from I, then that will be 1 minus 1 into x, so it is 0. So it maps whole of the set S1 cross 1 to 0. And on the other domain it is injective. So it is basically the mapping of this type. Now we have this circle, and this mapping maps all the points x here and t lying from 0 to 1, all the points of the type if x is here, say on the circle, then its image that lies on this line 1 minus t into x, and that varies, that depends on point t. If t is 0, then image of x0 is the point itself, this x, and if t is 1, then the point image is this 0, and if t is lying between 0 and 1, then the image 1 minus t into x that lies on this line joining 0 and x. So on whole of the set x cross I, sorry, on whole of the set S1 cross I, it is injective except for the set S1 cross 1, because for that set only the whole set goes to this point 0. So we can say S1 cross 1 maps to 0 under this mapping pi, and otherwise it is injective. Now we know capital H is a homotopy between H and a constant map. It means H of S1 cross 1, that is also a constant. So this is constant. So it means now we can induce a mapping K from B2 to X, which is extension of H, which is by the quotient map pi. So now let me explain it by a diagram. So now we can define K like this. So we have S1 cross 1, sorry, S1 cross I. So this is our, let us say, circle S1. This is S1 cross I. S1 cross I. So basically it is a cylinder, circle cross the closed interval 0, 1. Now we have a mapping capital H from S1 cross I to X. Say this is X. Now this is our given mapping H. And we have one more mapping. And let us say now this is B2. This is B2 and this is center of B2, 0. So now every line here in S1 cross I that maps to these type of lines. If this point is x0 and this point is x1 on this cylinder, then the image will go from this x to 0. Image of this line goes to this. Similarly, all the lines here in this cylinder, they go to the lines in this B2. So this is our mapping pi, which we have defined. And this capital H, this is homotopy, which is defined from S1 cross I to X. But we have to define a mapping K from B2 to X. So we define this K, which is extension of small h by this mapping pi. So we have to define K from B2 to X. Now how we define, let us say uh, this is h of S1, small h of S1, because small h maps S1 to X. So let us say this is image of the circle S1 under small h, and say this point is 0, not 0, basically this is a fixed point such that now we are saying this capital H is a homotopy. So basically capital H at S0, or we can say capital H at S1, that is this circle, and capital H at S1 cross 1, because we are saying capital H at S1 cross 1 is constant, and that we are taking as this point. So this point is basically capital H at S1 cross 1, which is a point, constant point in the space X. So basically we are saying that HS0, that is given by this circle, HS1, that is this point for every S in S1, and between that the points HXT, where T lies from 0 to 1, that lies here on these lines. So we will define a mapping, we will define the mapping K from B2 to X by this thing, that for this X, we have somewhere X here on S1. So for this X, we will map X to X and 0 to this point, H of S1 cross 1, and the line joining X to 0, that will be mapped to this line. Or we can say we define K from B2 to X by K of 1 minus X into T, where T is a point from 0 to 1 and X is a point in S1, that goes to capital H of XT. So we define K from B2 to X by this. Because we know every point of B2 is of the type 1 minus X into T, where X belongs to S1 and T belongs to I. So this K, this is extension of the given mapping H, and this is continuous also, because the capital H mapping is continuous map and K is defined in terms of H, so it is continuous map, and it is the extension of H, because when we take X in, when we take this point in S1, so when this point 1 minus X T belongs to S1, in that case, sorry, 1 minus x into t नहीं आएगा यहाँ पे 1 minus t into x, so it is 1 minus t into x. So if 1 minus t into x belongs to S1, then t is 0. In that case, k of 1 minus t into x, that will be basically h of x0, and h of x0 is just h of x, because this capital H, that is a homotopy. So when we take this point of domain of k in the set S1, then k of this point is just h of x. So we can say k is extension of h. So the second part is proved. Now we will prove 2 implies 3. So in 2 we have k, which is extension of h, and we have to prove that the fundamental that the homomorphism h star of fundamental groups, which is induced by h, that is actually trivial. So in this case we assume j from S1 to B2. This is inclusion map. Let us say j is inclusion map. Then H basically equal to the composition map K circle G, because K is a mapping from B2 to X, which is equal to H when it is restricted to S1. So H is a mapping from S1 to X, and K circle J, that is also a mapping from S1 to X. And since J is inclusion map, so J restricted to S1, that is just identity, and K restricted to S1, that is equal to H. So we can say H is just the composition K circle H. So it means H star is K star circle J star. And we know J star is trivial because J star is a mapping from fundamental group of S1 to fundamental group of B2. And we know fundamental group of B2 is just 0. It contains only one element, namely the identity element. So if the range space contains only one element, that means this mapping is just trivial mapping, just a constant mapping. So J star is a constant map. It means K star circle J star, that is also a constant map, because the range space of J star is trivial, and the range of that element under K star, that will be just a constant. So H star is trivial. Now we prove 3 implies 1. So in 3, we have assumed that H star is trivial, and we have to prove that H is null homotopy. So now let us assume P to be the standard covering map from R to S1, which we have proved earlier, that Px is equal to cos 2 pi x sin 2 pi x. So this is the standard covering map from R to S1. So let us say this is covering map. And we take P naught, this is the restriction of this mapping P to the unit interval I. So this P naught is basically P restricted to the unit interval I. Now this homotopy class of P naught. P naught is basically a path now, because domain of this P naught is I. So this is a path in S1. So the path homotopy class of P naught, this generates pi 1 S1 at B naught, because we know that first of all, this pi 1 S1 B naught, this is a group which is isomorphic to group Z, and group Z is cyclic. So this is generated by one element. And secondly, we know this P naught, this is a loop based at point B naught, where this B naught is a point 1 0 on the circle S1. And we know this P naught is a loop in S1, which begins and ends at B naught. So if this is a loop, then it will be an element which generates pi 1 S1 B naught, because this group is cyclic and generated by this loop. And this is a loop which lifts to R, which is beginning at 0 and ends at 1. So lifting of this loop P naught in R, that is a path beginning at 0 and ending at 1. So we can say like this, let us say this is R, so 0 and 1. So this is lifting of P naught, and this is our circle. This point is B naught. So P naught is the path which starts like this at B naught and ends at point B naught. So lifting of this path P naught, that is this path, when we have this P as a covering map. So now let us take x naught is image of the point B naught under the mapping H, because we know this is S1. Now let us say this is X. Now this is H. H is a mapping from S1 to X. So we take point X naught here, which is image of the point B naught. Now it is given to us that H star is trivial. H star is trivial, it means the loop F, which is H circle P naught. Now we know this P naught is a path from I to S1, and H circle P naught, this is from I to X. So this is a path. And secondly, P naught is a loop. So P naught at 0 and P naught at 1 both are same. So H of P naught, that is also a loop. So this is a loop starting and ending at point X naught. And this loop represents the identity element of pi 1x x naught. So this loop represents means it's homotopy class. So represents the identity element of the group pi 1 x x naught. So let us say this is the loop which starts and ends at x naught. Now if this represents the identity element of pi 1 x x naught, then there is a path homotopy between the path f and the constant path at point x naught. So let us suppose that path homotopy is capital F. So let capital F this be path homotopy between F and constant path at x naught. And now secondly, P naught into identity. P naught is a mapping from I to S1 and identity is from I to I. So we define a mapping I cross I to S1 cross I, which is actually P naught cross identity. And this is a quotient map because P naught is continuous closed surjective mapping and identity is also continuous closed surjective mapping. So it is a quotient map. And it maps 0 cross T to B naught cross T, because under the mapping P naught, image of 0 is B naught. B naught cross T, and also it maps 1 cross T to B naught cross T for each T in I. And otherwise it is injective, except for these two subsets 0 cross T and 1 cross T. This mapping P naught cross identity, this is injective mapping. And the path homotopy F, because F is a path homotopy between small f and the constant path. So F maps 0 cross I and 1 cross I to point x naught, because small f is a path based at x naught. So it maps 0 cross I and 1 cross I to point x naught of the path f, because f has both the endpoints equal to x naught. And secondly, because it is a homotopy between f and constant parts, so f of I cross 1, that is also x naught. So all these three, 0 cross I, 1 cross I, and I cross 1, I cross 1, they are x naught. So therefore, now there is a mapping there. Now these all things, they induce a continuous mapping capital H from S1 cross I to X, and this capital H, this will be a homotopy between the mapping H and a constant map. So we will explain it by diagram. So let us see how. Now we have this I cross I. Now this is I cross I. Let us say this is X. Now we have this point x naught, we have a loop here which is based at point x naught, and we have this mapping f, because f is a f is a path homotopy between the path f and a constant loop x naught. So this is, say, the path f, and this point is x naught, so capital F is a homotopy between them. So f of s0 goes to point fs on here, and f of s1 goes to this x naught. Then we have this mapping. Let us say this is S1, and we have this cylinder. This is S1 cross I. Now from I cross I to S1 cross I, we have this mapping P0 cross identity. And suppose this is the point B0 of the circle. So under this mapping P0 cross identity, P0 of 0 cross T, that means this line left edge, and P0 of 1 cross T, that means this right edge. These two go to point B0 cross T. So these two will go to this line B0 cross T. This left edge and right edge of the sphere I cross I, they go to this line B0 cross T. Otherwise it is continuous. Injective. Otherwise it is injective. So now we can define H from S1 cross I to X by these two mappings for all of the points except on this line B0 cross I. The points for all of the points on S cross I, because this mapping is isomorphism. This is basically quotient map, and this is injective on whole rest of the area except these two left and right edges, which maps to this line. So if we take any point in this S1 cross I except the points on this line, then the mapping is isomorphism, so its inverse image can be taken, and inverse image of any point lying in this cylinder, that will be in this sphere except for these two lines, and then image of that point will be taken to X under this mapping F. And when we take point on this line B0 cross T, on that line we will take the image as the point just x0, because we know the left edge and right edge, they go to x0 under this capital F. So we will define the mapping H by f of P0 circle identity inverse at any of the points of S1 cross I which are not in the subset B0 cross I, and we take H of B0 cross I to X0, and that H mapping, that will be homotopy from H0 to constant path. So this H will be a homotopy between small h and constant path. So if it is a homotopy between H and a constant path, that means H is null homotopy. So it completes the proof of the theorem. Now we have a corollary of this theorem. The corollary says the inclusion map J from S1 to R2 minus 0, this is not null homotopic. And secondly, the identity map I from S1 to S1, this is not null homotopic. So to prove this, we define a retraction R from R2 minus 0 to S1 by this Rx is equal to x upon norm x. Since we are taking the non-zero points of R2, so the norm of x, that is also non-zero, so we can divide x by norm of x, and x upon norm of x, that belongs to the unit circle S1. So this will be a retraction mapping of R2 minus 0 onto S1. And we have proved earlier that whenever J is inclusion map and R is a retraction map, then J star is injective. J star is injective. And injective map cannot be trivial. So this is non-trivial map, because we know the domain of J star is fundamental group of circle, and fundamental group of circle is non-trivial group. So this is also non-trivial mapping. So if J star is non-trivial, it means J is not null homotopic by the above theorem. Similarly, we can prove I star is non-trivial mapping, so I is not null homotopic, because I is a density mapping, so I star is also a density mapping, and a density mapping cannot be trivial, because again the domain is the fundamental group of S1, which is equivalent to integers. So similarly, we can prove I star is identity homomorphism and hence non-trivial, and therefore I is not null homotopic.